Hello everyone. I welcome you to this class of econometric methods. Myself, Dr. Muhammad Imdadul Haq, an associate professor at the Department of Economics, Aligarh Muslim University. We have been discussing the case of ordinary least squares method. We have seen what is beta, what is alpha, what is R square and things like these. In today's class, we will be doing the things practically. Meaning thereby we have a data in front of us. It's a purely hypothetical data. You can see that price is 1, 2, 3, 4 and 5. And the corresponding quantity demanded for price 1 it's 15, for price 2 it's 10, for price 3 it's 10, for price 4 again it's 10 and for price 5 it's 5. So we have taken a pure hypothetical data and we have tried to keep it simple so that our calculation is easy. Now, if we plot it on a graph or on x and y axis, you can see that when it is 1, when x is equal to 1, when x is equal to 1, your y is equal to 15. When x is equal to 2, y is equal to 10. When x is equal to 3, y is also equal to 10. When x is equal to 4, y is again 10. And when x is equal to 5, my y is also 5. So we get this point. This is called as a scatter diagram. So we have taken a raw data and we plot it in the form of a scatter diagram so you can have a feel of the data. Now we are going for the calculation. So first of all we take the mean of x, that is equal to 3. So 1 plus 2 plus 3 plus 4 plus 5 divided by 5. So that is equal to 15 divided by 5, that is equal to 3. Then we have taken the mean of y. So we add all these numbers 15 plus 10 plus 10 plus 10 plus 5 divided by 5. So that is equal to 10. In the next column we have done x minus x bar. X bar is equal to 3. So what we have done 1 minus 3, that is equal to minus 2, 2 minus 3 minus 1, 3 minus 3 0 and likewise. Next we have done the same process for y. So we have y is 15 and y bar is equal to 10. Y bar is equal to 10. So 15 minus 10, 5, 10 minus 10, 0, 10 minus 10, 0, 10 minus 10, 0, 5 minus 10, minus 5. So we have done with y minus y bar. Next, we have multiplied these two columns, that is x minus x bar and y minus y bar. So minus 2 multiplied by 5 minus 10, minus 1 multiplied by 0, here also 0, so we get 0, 5, 2 multiplied by minus 5, we get minus 10. Next we have done x minus x bar the whole square. So we have here x minus x bar. So minus 2 multiplied by minus 2, that is equal to 4. Minus 1 multiplied by minus 1, 1. 0 is 1. 1 multiplied by 1 is 1. 2 multiplied by 2 is equal to 4. So upon doing this, now we see the formula for beta hat. It is equal to, in the numerator it is summation x minus x bar y minus y bar. So here we have this summation x minus x bar multiplied by y minus y bar. The summation is minus 20. We write minus 20 over here. In the denominator it is summation x minus x bar square. We have this summation x minus x bar square, that is 10. We take over here in the denominator, this is x minus x bar square, 10. So minus 20 divided by 10, that is equal to minus 2. Similarly, Next, we have done the calculation of alpha hat. Alpha hat, the formula is y bar minus beta hat. The beta hat we have just now calculated multiplied by x bar. So we have y bar is 10, beta hat is minus 2 and x bar is 3. So when we do the calculation, it is equal to 16. Using this, we can write our estimated regression equation, which is equal to y hat is equal to, what is the value of alpha? 16. What is the value of beta? Minus 2 multiplied by x. So we have done the calculation of beta hat and alpha hat. Now we do the calculation of y hat. So in the first case, say 16 minus 2 multiplied by x is equal to 1. So 2 multiplied by 1 is 2. 16 minus 2, that is equal to 14. Next time it is 16 minus 2 multiplied by, what is the value of x? 2. So we write 2 over here. So now it is 2 into 2, 4. 16 minus 4, that is equal to 12. Next time the value of x is 3. So it is 16 minus 2 multiplied by 3. So 3 multiplied by 2, 6. 16 minus 6, that is equal to 10. Next time it is 16 minus 2 multiplied by, the value of x is 4. So 4 multiplied by 2, 8. 16 minus 8, that is equal to 8. And for the last term, it's 5 over here. So it is 16 minus 2 multiplied by 5. So 5 multiplied by 2, 10. 16 minus 10, that is equal to 6. So these are the calculations of y hat.
Screen recording.
Yeah.
Once came start.
So we have in this slide seen the calculation of beta hat, alpha hat and y hat. Next, now what was beta hat? What does beta hat represent? It represents the slope. It means that in a broad context, although there are other things, but generally we can say that when there is a 1 unit increase in the independent variable, I repeat, when there is a 1 unit increase in the independent variable, the dependent variable decreases by 2 units. Why decreases? Because here it is minus 2. The value of beta hat is minus 2. And what is my alpha hat? Alpha hat is equal to 16. It shows then when the value of the independent variable is 0, the value of the value of the dependent variable is equal to 16. If I draw a graph, it will be something like this. If this is the x-axis, this is the y-axis. This distance will be 16 and the slope of this line is minus 2. It is negative slope. The reason the value is minus 2 over here. Next, we go for the calculation of r square. See, we have seen already the calculation of y hat up till here. Now we are going for the calculation of r square. So for this we need to do some extra columns. That is y hat minus y bar. Y hat minus y bar. Y hat is here. Y bar we know is equal to 3. Y bar is the mean of y. So 14 y bar is, there is a correction over here. Y bar is not 3, it is equal to 10. There is a mistake. Please note this correction. So y bar is equal to 10. 14 minus 10, 4. 12 minus 10, 2, 10 minus 10, 0, 8 minus 10, minus 2, 6 minus 10, minus 4. Then in the next column, we do the square of it. 4 multiplied by 4, 16, 2 multiplied by 2, 4, 0 is 0, minus 2 multiplied by minus 2, it's 4, minus 4 multiplied by minus 4 is 16. One more column we required. See, we have already done the calculation of y minus y bar. We have already done this calculation. We need the square of it. So here it is 5. 5 multiplied by 5, 25. 0, it's 0, 0, it's 0, 0, it's 0. Again, minus 5 multiplied by minus 5 is equal to 25. So, we get these values. Now, what is the formula for r square? The formula for r square is equal to summation y hat minus y bar square, and this is nothing but y hat minus y bar square, that is equal to 40. And in the denominator it is y minus y bar square. Here we have y minus y bar square, we have done the summation of it, so it is 50. So 40 divided by 50, that is equal to 0.8. Now what does r square shows? It shows the proportion of the variance in the dependent variable that is being explained by its relationship with the independent variable. So here we can say 0.8 multiplied by 100, so that is equal to 80%. 80% of the changes in the dependent variable is caused by its relationship with the independent variable x. And the remainder, that is the 20%, this is not accounted for in this regression equation. Means 20% of the change in price is, 20% for the change in the quantity demanded is because of other factors, because of factors other than price. 80% change is because of price, and the remainder 20% of the change is because of factors other than price. It can be anything that is not covered here in this model. That is basically sitting in the, if it is y, if it is y is equal to alpha plus beta x plus e, so it is sitting in this error term. Now, we have done the regression, we have calculated r square. Now, is my r square significant? Meaning thereby, I have just taken a sample. I have not taken all the prices, I have taken a sample of prices and a sample of quantity demanded only. I don't have access to all the quantity demanded information and all the information on prices. I have taken for the sample. Now, is the estimated relationship which is shown by r square, and we are seeing that there is 80% relationship between these two, is this relationship applicable only for the sample? It is obviously for the sample because you have used a method and you have got a result, you have used a formula. But is it applicable for the entire population or not? Now, to test this, that is whether my estimated sample statistics is a representative of the population, real population parameter, we use F statistics. Now in F statistics, we need certain things. So see, y hat minus y bar whole square, this we have already done when we were doing the calculation of r square. Divided by k minus 1, here there are two variables, so 2 minus 1, that is equal to 1, so this becomes 40 divided by 1. So that is why we just write 40. In the denominator, it is y minus y hat. Y is this column and y hat we have estimated. So it is actual minus estimated. 15 minus 14, 1. 10 minus 2, minus 2. 10 minus 10, 0. 10 minus 8, 2. 5 minus 6 is minus 1. And then we do the square of it. 1 multiplied by 1 is 1, minus 2 multiplied by minus 2 is 4. 0 is 0, 2 into 2, 4, minus 1 into 1. So this is my column for y minus y hat whole square. Now we add of it, when the summation, it is 10. So beneath we write this 10. Now divided by n minus k, n is the number of items, 1, 2, 3, 4, 5. There are 5 sample observations, and k, there are 2 variables. So 5 minus 2, that is equal to 3. So in the denominator it is 10 divided by 3. So this value of F statistics, now we will have we will have our F distribution, we will get the table value from the statistical table. If this value it falls over in this region, then we say that our null hypothesis is that the relationship is not significant and the alternate relationship is significant. So if it falls over here, we say that our R square is significant. R square is significant, and if this value it falls over here, my R square is not significant. Or here we are accepting, in this case we are accepting the null hypothesis that there is no significant relationship, and here we are rejecting the null hypothesis that is there is a significant relationship. After this, we move to the next concept, that is the standard error of U. Now, standard error of U, the thing which you need is, already we have done the calculation when we were doing our F ratio. That is, we have this y hat, then we did y minus y hat. We have already done in our previous slide, and then we did the square of it. The summation of it is equal to 10. So 10 divided by n minus 2, because there are two items and n is equal to 5. So 10 divided by 3, that is equal to 1.825. This is the standard error of U. We need this in the for testing for the significance of the individual coefficient, that is for beta. Now, once you are done with this calculation of standard error of the regression, standard error of U, of the error term, then we go for a standard error for beta. The standard error of beta is nothing but the standard error of U divided by under root summation x minus x bar whole square. X minus x bar whole square, we have done the calculation when we were doing the calculation of B. There in the denominator term is the same. So we have 1.825 divided by under root 10. So this is equal to 0.547. So we get this. Now we go for the calculation of T statistics. T asterisk or the T statistics is nothing but beta hat. Our beta hat we have seen is equal to minus 2 divided, this is the minus 2 over here, divided by the standard error of beta, that is equal to 0.547. So we get a value minus 3.65. Now when we get a value of minus 3.65, again we go to our statistical hypothesis testing process. The value normally, so the value of this portion, it is plus 2.776, and the value over here it is minus 2.776, and our null hypothesis is that the population beta is equal to 0 against the alternate hypothesis that the population beta is not equal to 0. Now what is our calculated value? Our calculated value, if you remember, T asterisk is equal to minus 3.65. So 3.65 will fall over here. No, excuse me. It is minus 3.65. There is a small amount of correction. So minus 3.65 will fall over here. Minus 3.65. In this region, you reject the null hypothesis, that is the population beta is equal to 0, and you accept the alternate hypothesis. That means that the population beta is not equal to 0, or we can say that the value of beta is significant. If say our value was somewhere over here, if suppose our T value was equal to minus or plus 1.25, then it would have fallen in this region. This is the in this region the null hypothesis is accepted and the alternate is rejected. Null hypothesis accept means the population beta is equal to 0, meaning thereby the beta which we have calculated through our method of OLS which we have calculated is not significant. So this is the region of significance, here also significance. This region is the region of not significance. Next, we have also seen the concept of confidence interval. So in confidence interval, we simply do beta hat, that is your beta hat is equal to -2. Then the t value, because we are doing it at 5% level of significance, so it is divided into two parts. So t, that is why we write it 0.025, means half of 0.5 multiplied by the standard error of beta. So this is the lower limit, and the upper limit is b hat plus. In the lower limit it is minus, in the upper limit it is beta hat plus t at 0.025 multiplied by the standard error of beta. So we know that the t value, we have seen in our previous slide also, is equal to 2.776, and the standard error of beta is equal to 0.547. So we do -2 minus this term, that is 2.776 multiplied by 0.547. So we get a value -3.5187, and for the upper limit, so we have -2 plus 2.776 multiplied by 0.547, and we get this term -0.48153. So our confidence interval, that is beta, it lies between this -3.5 to -0.48. This is the concept of confidence interval. So finally, we will see that we started with this data. We calculated y hat. In our case, we used 16 as an intercept and term and -2 as our slope coefficient, and we got the value of y hat. Now, these scatter diagram, these scatter plots we have seen earlier also. It was 15, here 10, 10, 10, 10, and then for this case it was 5. So this we have seen at the start of our class. Now this is y hat is nothing but my regression line. Now let us see, when it is 1, y hat is 14. When x is equal to 1, y hat is 14. We get this point. When x is equal to, y hat is 12. When x is equal to 2, y hat, we get a point 12. See, here it is 12. When x is equal to 3, y hat is equal to 10. X is equal to 3, y hat is equal to 10. Earlier also it was 10. Here also it is 10. Now when x is equal to 4, it is 8. The actual value is 10, but the estimated value is 8. Here it is 8. We get this. And last, when x is equal to 5, the actual value is 5, but the estimated value is 6. If we join these points of estimated as shown by the blue dotted lines, excuse me, my freehand graph is not exactly straight, but if you just see the blue line, your blue line is exactly straight line, because we are estimating a linear relationship. So it's a straight line, and this straight line is what is your regression line. So our purpose is to find a regression line, or find a straight line wherein the slope will be the same. The slope is -2, and here also the slope is -2. Here also it is -2, here also it is -2. So since it's a straight linear line, so the slope would be the same. So the slope is equal to -2 of this line, and if I extend this line, this will go over here. That is the intercept. This is my alpha hat. Your intercept is 16, your slope is -2, and this line fits this scatter plot. This is scatter plot of this diagram in the best way. In the best way meaning thereby in the way wherein the errors are being minimized. So this was just a practical demonstration of the concepts which you have learned earlier. Herein we have numerically solved a question in order to show you the calculation of beta hat, alpha, r square, f ratio, standard error of u, and then the t statistics, and finally we have drawn the regression line and show you what is basically a regression, basically a regression process wherein we are fitting a line to a data set in such a way that we minimize the errors, and with this line it can be proved that this is the best fit line. With this, I thank you. Hope this lecture was clear to you. Goodbye.